Empirical distribution function, Wikipedia audio. In statistics, an empirical distribution function is the distribution function associated with the empirical measure of a sample. This cumulative distribution function is a step function that jumps up by 1/n at each of the n data points. Its value at any specified value of the measured variable is the fraction of observations of the measured variable that are less than or equal to the specified value. The empirical distribution function is an estimate of the cumulative distribution function that generated the points in the sample. It converges with probability 1 to that underlying distribution, according to the Glavenko-Cantelli theorem. A number of results exist to quantify the rate of convergence of the empirical distribution function to the underlying cumulative distribution function. Let be independent, identically distributed real random variables with the common cumulative distribution function f. Then the empirical distribution function is defined as definition, where 1, a, is the indicator of event A. For a fixed t, the indicator 1, x, I, less than or equal to t, \lec t, is a Bernoulli random variable with parameter p equals f, hence, n, f, n, t, is a binomial random variable with mean nf and variance nf. This implies that f, n, t, is an unbiased estimator for f. However, in some textbooks, the definition is given as f, n, t, equals 1, n, plus 1, I, equals 1, n, 1, x, I, less than or equal to t, equals \sum\math\lec t. The mean of the empirical distribution is an unbiased estimator of the mean of the population distribution. The variance of the empirical distribution times n, 1, is an unbiased estimator of the variance of the population distribution. Since the ratio /n approaches 1 as n goes to infinity, the asymptotic properties of the two definitions that are given above are the same. By the strong law of large numbers, the estimator, f, n, t, converges to f as n almost surely, for every value of t. Thus the estimator, f, n, t, is consistent. This expression asserts the pointwise convergence of the empirical distribution function to the true cumulative distribution function. There is a stronger result, called the Glavenko-Cantelli theorem, which states that the convergence in fact happens uniformly over T. The subnorm in this expression is called the Kolmogorov-Smirnov statistic for testing the goodness of fit between the empirical distribution, f, n, t, and the assumed true cumulative distribution function f. Other norm functions may be reasonably used here instead of the subnorm. For example, the L2 norm gives rise to the Kramer-von Mises statistic. The asymptotic distribution can be further characterized in several different ways. First, the central limit theorem states that pointwise, f, n, t, has asymptotically normal distribution with the standard, n, rate of convergence. Small sample properties. This result is extended by the Donskir's theorem, which asserts that the empirical process, n, f, viewed as a function indexed by t, r, converges in distribution in the Skorokhod space D, plus, to the mean zero Gaussian process, g, f, equals, b, f, equals B backslash CIRCF, where B is the standard Brownian bridge. The covariance structure of this Gaussian process is: the uniform rate of convergence in Donsker's theorem can be quantified by the result known as the Hungarian embedding. Alternatively, the rate of convergence of N, F can also be quantified in terms of the asymptotic behavior of the subnorm of this expression. Number of results exist in this venue. For example, the Dvoretzky-Kiefer-Wolfowitz inequality provides bound on the tail probabilities of N, F, backslash. In fact, Kolmogorov has shown that if the cumulative distribution function f is continuous, then the expression N, F, backslash converges in distribution to B, which has the Kolmogorov distribution that does not depend on the form of f. Another result, which follows from the law of the iterated logarithm, is that and asymptotic properties